To calculate the voltage drop at the end of a 35-kilometer line with a voltage of 13,800 volts, 100 square millimeter conductors, and a 100 amp current in a three-phase system, we need to follow these steps. Firstly, calculate the resistance represented by a letter R. The formula for resistance is R equals ρ times L divided by A, where ρ is the resistivity of copper, which is 0.1724 ohms square millimeters per meter. L is the length of the line, which is 35 kilometers or 35,000 meters, and is the cross-sectional area of the conductor, which is 100 square millimeters. Plugging in the values, R equals 0.1724 ohms square millimeters per meter times 35,000 meters divided by 100 square millimeters. Therefore, R is approximately 6.37 ohms. Secondly, calculate the reactive impedance represented by the letter X. The formula for reactive impedance is X equals 2 pi FL times inductance per unit length, where F is the frequency of the system, which is 50 Hz or 60 Hz. L is the length of the line, which is 35 kilometers or 35,000 meters, and inductance per unit length is approximately 1.2 millihenries per kilometer. Plugging in the values, X equals 2 pi times 50 Hz times 35,000 meters times 1.2 millihenries per kilometer. Therefore, X is approximately 424.12 ohms. Thirdly, calculate the impedance represented by the letter Z. The impedance Z is the complex sum of resistance R and reactive impedance X. The formula is Z equals the square root of R squared plus X squared. Plugging in the values, Z equals the square root of 6.37 squared plus 424.12 squared. Therefore, Z is approximately 424.22 ohms. Fourthly, calculate the voltage drop represented by the term V drop. The formula is V drop equals I times Z, where I is the current in a line, which is 100 amps, and Z is the impedance, which is 424.22 ohms. Plugging in the values, V drop equals 100 amps times 424.22 ohms. Therefore, V drop is approximately 42,422 volts. In conclusion, the voltage drop at the end of the 35-kilometer line with 13,800 volts voltage, 100 square millimeter conductors, and 100 amp current is approximately 42,422 volts. This voltage drop is significantly larger than the original voltage, indicating a major problem. In practical power systems, voltage drop should be kept within a small percentage of the source voltage to maintain stable and efficient operation. A voltage drop of 42,422 volts on a 13,800 volts line is not acceptable. It signifies that the current carrying capacity of the chosen conductor is inadequate for the length of the line, or that there are other issues, such as excessive loading or impedance. To mitigate such a large voltage drop, several strategies can be considered. Firstly, increasing the conductor size will reduce the resistance per unit length, thus lowering the overall voltage drop. Secondly, using multiple parallel conductors can effectively increase the overall cross-sectional area, thereby reducing resistance and voltage drop. Thirdly, reducing the line length, if feasible, will proportionally decrease the total resistance and reactive impedance. Fourthly, installing voltage regulators along the line can help maintain the voltage within an acceptable limit. Fifthly, using transformers to step up the voltage at the sending end and step it down at the receiving end can reduce the current in a line, thereby reducing voltage drop, since losses are proportional to the square of the current. Sixthly, power factor correction can improve the efficiency of the system by reducing reactive power losses, thus decreasing the overall current and voltage drop. To accurately determine the best solution, a detailed power system analysis is essential, taking into account load characteristics, line parameters, and regulatory requirements. It is important to ensure that any modifications comply with applicable standards and regulations, such as those established by the National Electrical Code or equivalent standards. The calculations provided are based on simplified assumptions and do not account for factors such as skin effect, proximity effect, temperature variations, and the presence of harmonic currents, all of which can influence the actual voltage drop. For more precise results, it is advisable to use specialized power system simulation software that can model these effects. Moreover, the inductance per unit length value used, 1.2 millihenries per kilometer, is an approximation. The actual inductance depends on conductor spacing, conductor configuration, and the presence of nearby grounded objects. Therefore, obtaining accurate inductance values from conductor manufacturers or using field measurements can improve the accuracy of voltage drop calculations. Additionally, in three-phase systems, the voltage drop calculation can be more complex due to phase imbalances and the presence of neutral currents. In such cases, it is necessary to perform a full three-phase power flow analysis to accurately determine the voltage drop in each phase. Furthermore, the impact of the load on the voltage drop should be carefully considered. Loads with high inrush currents, such as motors, can cause significant voltage dips during startup. Similarly, nonlinear loads, such as electronic devices, can generate harmonic currents that increase losses and voltage distortion. These effects can be mitigated by using appropriate load management techniques and harmonic filters. Finally, it is important to note that the voltage drop calculation is only one aspect of power system design. Other factors, such as thermal ratings of conductors, short circuit capacity, and system stability, should also be considered to ensure a safe and reliable power system. Consulting with experienced electrical engineers and power systems specialists is highly recommended for complex projects. Keep in mind that a practical power system should maintain a voltage drop within a small percentage of the source voltage, typically around 5% or less, to ensure proper operation of connected equipment and avoid voltage-related problems.